So now that you have seen all of the trigonometric ratios and their names, for instance, sine of theta is equal to y over r, we're now going to be able to see the relationship between all 6 of those relationships, so that if we know something about one, we'll be able to find information about another. So the way that we're going to be approaching this is by referring back to our original ratios. So keep in mind that sine of theta is y over r, and cosecant of theta is its reciprocal. We can see that cosine of theta is x over r, and secant of theta is its reciprocal. And finally, tangent of theta was y over x, so cotangent of theta was its reciprocal. So it should be pretty easy to be able to find reciprocals if we end up knowing one of the quantities. So let's just say that sine of theta is 2/3. Cosecant of theta would be 3/2. All right, well, we also learned how to find each of these trigonometric ratios within each of the quadrants. But now I want to give a quick, easy way to be able to determine at least what the sign of these values is going to be, positive or negative, in each quadrant. So let's start off by keeping in mind that this is the x-axis and this is the y-axis. But more specifically, this is our positive x direction, while the left is going to be our negative x direction. And if moving upwards is our positive y direction, moving downwards is, of course, our negative y direction. Which tells us a few things here. Since we want to be able to determine what x, y, and r are going to be in each of these quadrants, keep in mind that r is always simply a directed distance to some location. So if this is r is always positive no matter what. And so now we just have to keep in mind what x and y are going to be. So let's take a look over here in the first quadrant and realize that in quadrant 1, x is positive and y is also positive. Which really means that if x, y, and r are all positive in this first quadrant, in quadrant 1, okay, then we know that every one of these ratios over on the left is also going to be positive in the first quadrant. Well, let's say we went to quadrant 2. Now we should realize that x is going to be negative in quadrant 2, while y is going to be positive because it's above the x-axis. So now if we take a look at each of these ratios individually, we should realize first of all that y over r will be positive, but x over r will be negative and y over x will also be negative. So if we want to determine which ratios are positive, okay, then maybe we should scroll here and just ask that question down below. Which ratios are positive in each quadrant? So we should see that in the first quadrant, all ratios are going to be positive, while in the second quadrant, only sine of theta is positive. Okay, so why don't we go ahead and state then that sine theta is greater than 0. While all ratios over here are greater than 0. Now we're only going to be dealing in this diagram with sine, cosine, and tangent, because if sine is positive, then obviously its reciprocal will also be positive. If tangent is negative, then cotangent will also be negative. So we're only going to deal with sine and cosine, and then we can add the others later. So let's go ahead and take a look then back at quadrant 3. So now in quadrant 3, we should realize that x is negative, but so is y. So both values of x and y are both negative. Keep in mind, though, that r is always positive. So if I take y over r, then that quantity would be negative. Sine of theta would be negative in the third quadrant. X over r is a negative over a positive, so that would also be negative in the third quadrant. But now if I take a positive or a negative divided by a negative, then that shows the tangent of theta will be positive in the third quadrant, which means that in the third quadrant, tangent of theta is positive. Okay. And so we can see that in the first quadrant, all of the ratios are positive. In the second quadrant, only sine is positive. And in the third quadrant, tangent is the only positive ratio. So now let's go ahead and take a look at the fourth quadrant. You might be able to guess what's going to happen here. But now we should recognize that x is positive. But now we're below the x-axis, so y is negative. And now if we take a look back again, a negative divided by a positive is a negative. Negative divided by a positive is also a negative. But now when you take a look at a positive divided by a positive, now I see that cosine of theta is going to be positive over here. So there's a very simple way to remember which ratios are positive or negative without having to draw the triangles or without having to actually really think through this process. Okay, there's an acronym referred to as ASTC, or in other words, all students take calculus, or at least trigonometry students will, because that's the next logical step. Okay, so all students take calculus, ASTC. What that indicates here is that in the first quadrant, A stands for all are positive. In the second quadrant, S stands for sine is positive. In the third quadrant, T stands for tangent is positive. And in the fourth quadrant, C, meaning cosine, is the only positive. So if we refer to, say, the second quadrant, and I'm trying to find sine of an angle, I know my answer will be positive. But if I'm trying to find tangent of an angle in the second quadrant, I know my answer is negative. So notice that this acronym just simply shows us that this is sine, this is tangent, and this is cosine. Okay. So with that said, we should also recognize that this implies that cosecant of theta in the second quadrant will also be positive because it's the reciprocal of sine. That also indicates that cotangent of theta in the third quadrant will be positive. And it also indicates that secant of theta in the fourth quadrant will be positive. But we just memorized sine, tangent, and cosine so that we can recall what the ratios are going to be in each. So now if we look back to the individual reciprocal, the reciprocal ratios here, I'd like to demonstrate some relationship between these. So these are two different ways to memorize. We could memorize, that sine theta is equal to the y value over the r value. Or we could actually see how sine theta relates to other ratios without using x, y, and r. For instance, let's just take a look at the fact that sine of theta is equal to y over r. Okay. Well, let's just take a look now at the reciprocal of sine theta. The reciprocal of sine theta is 1 over y over r. which by algebra is just 1 times r over y, which is actually just r over y. Well, the reason this is important is because it demonstrates now that this quantity is really 1 over sine of theta. And what we've just proven using algebra is that 1 over sine theta is actually equal to the value of cosecant of theta. And what we have just derived is one of 6 reciprocal identities. These reciprocal identities, as we see in this table here, are just simply showing us the relationship on how we can actually describe each of the relationships between sine and cosine by just writing it as its corresponding reciprocal. So if I ever see sine of theta, I could rewrite that as 1 over cosecant of theta. And likewise, I could rewrite cosecant of theta as 1 over sine of theta. Since these are reciprocals of each other, secant and cosecant, or secant of theta and cosine of theta, we can write them as their reciprocal identities. So the reason why this is beneficial is in finding values by being given one ratio. So let's just say, for example, that we are given that cosecant of theta, is equal to the negative of root 12 over 2. And we want to find sine of theta. Well, we should realize by this reciprocal identity that we're able to just simply take the reciprocal of cosecant theta to find sine theta, but we want to write the notation accurately. So keep in mind that sine of theta is equal to 1 over cosecant of theta. And we're already told what cosecant of theta is. So therefore, this is 1 over the negative of root 12 over 2. Which, again, by algebra, simply becomes negative 2 over root 12. Now, I would like you to notice that the numerator up top here was negative, but now I didn't move that negative onto the bottom. I very well could have. That means the exact same thing, but it's pretty standard for us to just put the negative in the numerator. You could also choose to put the negative in front of the whole fraction. Either way you choose to do it, it doesn't matter, but you would have to recognize which of these two values is going to be the negative or positive when it comes time to finding other values, okay? But notice that it's not enough for us to be able to write negative 2 over root 12 because we need to rationalize the denominator in trigonometry. So we're going to multiply by root 12 over root 12. And this ends up giving me negative 2 root 12 over 12. Now this still, again, isn't quite simplified enough because I could cancel out a 2. And this gives me negative root 12 over 6, which is better. But we'd like to keep in mind that this is not quite correct either, because we should always be simplifying our radicals. So not only do we rationalize denominators, but we also need to recognize that root 12 is the same as the square root of 4 times 3. So root 12 is actually negative 2 root 3 over 6. And with that, we can now finally say that sine of theta is the reciprocal of negative root 12 over 2, which is negative root 3 over 3. So although it was a really quick step to just say that sine theta was the reciprocal it still took work to be able to simplify that quantity algebraically. Now at this point, we'd like to determine what the ranges of the trigonometric functions are, which means what are the possible values or the possible outputs of each of these 6 trigonometric functions. So one thing to recognize in this diagram over on the right is that R is the hypotenuse. And the hypotenuse of any right triangle is always the longest side. So that means that there's a couple of things to recognize here. Y is always less than R, and X is also less than R. Now, Y and X could be sometimes Y depending on what the angle is. Sometimes Y would be much shorter than X. Sometimes Y would be much longer than X. So Y and X, Y could be larger than X could be larger than Y. But one thing that we know with certainty all the time is that Y is less than R. Now that's important because if we take a look back to sine theta, if the numerator is less than the denominator, then that means that this ratio is always less than 1. And likewise here with cosine theta, if X is always less than R, then the numerator is always less than the denominator, which means that this quantity or this fraction is always less than 1 as well. So that's something really important to recognize because that implies that sine theta is automatically less than 1. But let's be very careful because what if we were actually on this quadrantal angle? Okay, on this angle, notice that Y is 0 and R is 1 still, which implies that sine theta is 0. That would make sense. But what if this angle ended up becoming 90 degrees? In this situation here, we should recognize that Y is equal to 1, but R is also equal to 1. So at certain angles, namely at 90 degrees, it's possible for sine of theta to be equal to 1. So sine of theta will always be less than or equal to 1, and cosine of theta, for the same reason, will also be less than or equal to 1. But we also have to be very careful here, because if we were looking at a different quadrant, sometimes sine of theta and cosine theta are going to be negative values. So if we happen to be back in the second quadrant, now notice that the ratio itself would still be less than 1, but it would be negative. So in this particular case, we should recognize that sine of theta has to be somewhere between -1 and 1. Believe it or not, this is an extremely important aspect of trigonometry. The values of sine theta and cosine theta are always fractions that are less than 1. It's just that sometimes they could be positive or negative. Now, what we should recognize about that is that if we look at the reciprocal functions, meaning cosecant of theta, okay, cosecant of theta would imply that now the numerator is larger than the denominator. Anytime we have a situation where the R value or the numerator is larger than the denominator, then we get an answer that's larger than 1. So that must mean the cosecant of theta would have to be larger than 1. But keep in mind that if it was negative, there could be another option as well. If Y happened to be negative, now I might have something like 2 over -1, which would mean the cosecant of theta is -2. -2 is not bigger than 1. So what we mean is that it has to be everything other than what sine theta is. So if you think of a number line, if sine theta is somewhere between -1 and 1, then cosecant of theta is the reciprocal. So it's everything less than -1 or greater than 1, which is why the second option is that cosecant of theta could be less than or equal to -1. That same exact scenario happens for cosine, to where secant of theta has to be greater than or equal to 1, or the value of secant theta would have to be less than or equal to -1. Secant of theta would have to be less than or equal to -1. Okay, so far these are a couple of important components that we have to recognize. The last ratios we want to take a look at are tangent of theta and cotangent of theta. So keep in mind that each of these ratios only deal with y and x. So r never comes into play when we're dealing with tangent and cotangent. So since we're looking at the values that x or y over x and x over y can take on, keep in mind that in order to be less than 1, the numerator is less than the denominator. In order to be greater than 1, the numerator is greater than the denominator. So considering x could be bigger than y or y could be bigger than x, that must mean that tangent of theta and cotangent of theta can virtually take on anything we want, which is why tangent of theta could be anything between -infinity and infinity. And the same thing for cotangent of theta. It can also be any quantity between -infinity and infinity. So the important ones here to recognize are sine and cosine specifically. Okay, not to say that the other ones are not important, but the values of sine and cosine, when you calculate those, must be ratios between -1 and 1. Now let's just take a look at a couple of possible values for sine and cosine real quick. So let's look at a couple of possible values. It's possible for sine of theta to equal 1/2. It's possible for cosine of theta to equal -√2/5, because that's also greater than -1. It's possible for sine of theta to equal 1, because it's still less than or equal to 1. But let's just take a look at a couple of impossible values. I know that it's impossible for sine of theta to ever equal -2. It's impossible for cosine of theta to ever equal √3. What we've got to recognize here is that these values can never occur. So if they do, something went wrong, or there's no angle that would cause that to happen. In terms of cosecant of theta, let's look at a couple of things that are possible. Cosecant of theta could be -10. Secant of theta could be anything bigger than 1 or less than -1. So maybe the square root of 17. Those are possible. But what's not possible is for cosecant of theta to be equal to 1/2. Because cosecant of theta can't be between -1 and 1. Secant of theta, it's impossible for secant of theta to ever be a value of -√2/5. It's impossible because it has to be somewhere bigger than 1 or less than -1. But without writing what's possible and impossible for cotangent and tangent, there is virtually nothing that is impossible here. We realize that the values of tangent of theta will always yield values between -infinity and infinity. Now we have a few other relationships between the trigonometric ratios. Again, these are called identities. Identities are something that are true for all angles that you give. No matter what angle you give, the reciprocal identities are always true. For instance, no matter what, sine of theta is always equal to 1 over cosecant of theta. Or secant of theta is always equal to 1 over cosine of theta. This is just based off of algebra with these ratios. Well, there's some other identities as well that we're going to investigate at this point. These are referred to as the Pythagorean identities. So I'd like to start off by just demonstrating the Pythagorean theorem for this standard triangle, which shows that x squared plus y squared is equal to r squared. Now it's pretty important to recognize that this is the Pythagorean theorem, but there's different ways that we could write this as well. We could actually cause one of these to equal 1, one of these terms to equal 1, by dividing by itself. So let's decide to convert the right side into a value of 1. That means that we could divide by r squared. But that would imply that we'd have to divide everything by r squared in order to make it equivalent. Well, now we could recognize that because each of these have a numerator and denominator being squared, we could write this as x over r squared plus y over r squared equals 1. But what we should recognize about this is that this is the same thing as cosine of theta squared. And y over r is the same thing as sine of theta squared. And so what we've done is we've taken side lengths of this triangle by using the Pythagorean theorem and converted into trigonometric functions. And so this is considered a Pythagorean identity. More specifically, exponents above trigonometric functions can actually be written up above the word. So we could write this as cosine squared theta plus sine squared theta is equal to 1. And this is considered a Pythagorean identity. This is a really helpful and important tool because now this is showing us that anytime we're dealing with a problem where we see the sum of both cosine squared theta and sine squared theta, we could eliminate it and just replace that sum with 1. And believe it or not, it comes up a lot more than you would expect. I'd like to look at another relationship here. In the last problem, we decided to set the right side equal to 1, but we really could have set any one of these quantities equal to 1. So let's go ahead and take a look at another one where we decide to divide out, let's say, r squared, or x squared rather. Okay. Well, if I divide that quantity by x squared to make it equal 1, I could divide each of these by x squared as well, and now rewrite the result. This gives us 1 plus y over x quantity squared, which is equal to r over x quantity squared. But now notice that those are some common ratios as well. Y over x is the same as tangent. So we could rewrite this as 1 plus tangent squared theta is equal to secant squared theta. And sometimes we choose to rearrange this to where you could rewrite it by subtracting the tangent squared theta. And the way that I've always learned this and memorized it is by setting all of these relationships equal to 1. So now this shows us that secant squared theta minus tangent squared theta is always equal to 1. So again, what this is demonstrating is anytime let's say that we have a value of tangent theta and we're trying to find an answer for secant of theta. We now have a relationship that compares those two ratios. So by knowing one ratio, we could find the other ratio. Same thing up in this one. If we know cosine of theta and we want to find sine of theta, we could simply just plug in the ratio for cosine. And there's one last relationship as well. So let's start with x squared plus y squared equals r squared again, the standard Pythagorean theorem. And if we now decide to divide by y squared to make that term equal to 1, then we could make this divided by y squared and divide this by y squared. And this gives us x over y quantity squared. This second term is 1. And now over here we have r over y quantity squared, which again are a few of our ratios from our triangle. We should see that x over y is cotangent squared. Is cotangent theta. So we say cotangent squared theta plus 1 equals cosecant theta squared, or rather cosecant squared theta. So that's another Pythagorean identity. Cosecant squared theta can be replaced with cotangent squared theta plus 1. There's lots of ways to convert these, by the way. Okay, so make sure that you're recognizing all the different ways that these can be written. But in general, a lot of times what we do is we isolate the 1. So we could subtract cotangent squared theta, which gives me cosecant squared theta minus cotangent squared theta is equal to 1. And here's our last Pythagorean identity, which again tells us that if we know one of these two ratios, if we know the value of cosecant theta, we can use this ratio to find the value of cotangent theta. Now, a couple of things to note here. If I were to rearrange this, I could rearrange this by subtracting sine squared theta and isolating cosine squared theta. There's going to be a lot of different ways for this, these identities to be written. But if we just memorize these three that are in yellow, then we're going to be set for the rest of these. I could isolate sine squared theta as well by simply subtracting cosine squared theta. 1 minus cosine squared theta. Or if you look at this one here, we could see we've already got cosecant squared theta as one of our options. We could also come up with another one by isolating cotangent squared theta, okay, which gives me cotangent squared theta is equal to cosecant squared theta minus 1. So you could see the order in which we write them, the signs that we use are really important. So a couple of things to just note for these Pythagorean identities. One thing to note is that the identity involving sine and cosine has a plus sign in between. It's a sum. So cosine squared theta plus sine squared theta is equal to 1. While the other two are still equal to 1, but they have minus signs. And that's a really important thing to remember and memorize. One thing to help us with these two is that if you memorize one of them, secant squared theta minus tangent squared theta equals 1. Now you just add co to the front of these, and you have cosecant squared theta minus cotangent squared theta equals 1. So all three of these are going to be important, but we also want to make sure that we can convert from one form to another. So we want to note one notational issue that often arises here. So when we talk about cosine squared theta, the fact that the exponent of 2 is above the cosine is demonstrating that we are squaring the ratio cosine. So we're taking cosine theta and multiplying by itself. One thing to note here is that cosine theta squared is not equal and cannot be written as cosine theta squared, because now it looks like the exponent is above the theta. which would mean that we're squaring the angle and then taking cosine of that value, which is going to be much different than cosine squared theta. Okay, so let's take a look at an example. Let's assume we have an angle that's in quadrant 2. And we're also told that sine of theta is equal to 2/3. We'd like to find the other trigonometric ratios if possible. So starting off with the fact that sine of theta is 2/3, I'm going to start to talk you through a few things that I know. I know that cosecant of theta is the reciprocal. So I know the cosecant of theta can be found by taking the reciprocal of sine theta. The reciprocal of sine theta is 3/2. So I now know that cosecant of theta is 3/2. All right. Well, what else can I do? I also have another identity, okay? There's another identity that relates sine theta to some other function, and that identity is a Pythagorean identity. The fact that sine squared theta plus cosine squared theta is equal to 1. But if I know that sine of theta is 2/3, then I can replace sine theta with 2/3. And now notice that the only unknown is going to be cosine squared theta. Okay, well, simplifying and doing a bit of algebra here, we've got 4/9 plus cosine squared theta is equal to 1. Which, if we subtract 4/9 from 1, we get 5/9. And now notice that if we take the square root of both sides, we're about ready to find what cosine theta is. Cosine of theta is equal, well, I take the square root of top and bottom and I get the square root of 5/9. But be careful, because when I take the square root of two sides of an equation, I've got to realize that the answer could be either plus or minus the square root of 5/9. I'm sorry, 5/3, because it's the square root of 9, okay? So now we have to question which one is it? And this is where we go back to the fact that theta is in quadrant 2. You might remember that we learned about ASTC, right? The little short trick to remember which functions are positive and which quadrants. So since we're in quadrant 2, we know that sine theta is positive, which implies that cosine of theta is negative and tangent of theta is negative. So for this particular problem, we've got to recognize that the cosine value that we're looking for is negative √5/3. And therefore, we've got our value of cosine theta. It's negative square root of 5/3. Now that we know cosine of theta, just keep in mind that we could find the reciprocal pretty easily, right? We could see that the secant of theta is equal to the reciprocal of cosine theta, which means that it's simply -3/5. But that's not good enough because we need to rationalize the denominator, which tells me that my secant of theta is -3/5/5, which validates the fact that my secant of theta should also be negative, just like my cotangent of theta should also be negative. So this gives us -3/5/5. So we've just got a couple more functions to find. We need to find somehow tangent theta and cotangent theta. The problem is that I can't find cotangent before knowing tangent using the reciprocal identities and vice versa. But what we can do is refer back to a couple of our Pythagorean identities. If I know secant of theta, I could find tangent of theta. Or if I know cosecant of theta, I could find cotangent of theta. So either one of these is fine. Let's just go ahead and use our first identity. Secant squared theta minus tangent squared theta equals 1. So using this identity, now that we know secant of theta, will help us to find tangent theta. I know that secant of theta is the negative of 3 root 5 over 5 squared minus tangent squared theta equals 1. Well, let's go ahead and square, and notice that when I square the left side, squaring a negative makes it positive. So the numerator is 9 times 5, or 45. 45 divided by 5 is 9. Minus tangent squared theta equals 1. And now if I want to get tangent squared theta alone, I'm going to subtract 9, which gives negative 8. But then I have to divide by a negative to get tangent squared theta to be positive. And now I'm left with tan squared theta equals 8. So I can now take the square root of both sides, which tells me that tangent of theta is plus or minus 2 times the square root of 2. That's the square root of 8. But again, which one is it going to be? This goes back to the fact that theta is in quadrant 2, which means that my tangent value has to be negative. So that means that tangent theta is equal to the negative of 2 root 2. So we could fill in tangent theta is negative 2 root 2. So the last thing to recognize then is, how do we find cotangent theta? Well, keep in mind, if we know the reciprocal, we can see that cotangent theta is 1 over tangent theta, which is 1 over negative 2 root 2, which would normally be fine, except for the fact that the denominator has a radical. So if I multiply by root 2 over root 2, then that's going to give me a value of negative root 2, negative root 2, and on the bottom, 2 times 2 gives me a value of 4. So we've got negative root 2 over 4. And look at the benefit of this. All we knew at the very beginning was one of the 6 ratios, as well as where that angle was located. And we were able to find all 5 of the other trigonometric functions by simply using identities, reciprocal identities and Pythagorean identities. At this time, we have 2 last identities that are beneficial to be able to find trigonometric ratios if we know 1 or 2 of them. So let's take a look at sine theta and cosine theta. If I were to divide these two, sine theta divided by cosine theta, let's see what that would actually do. That would mean that I would be dividing y over r by x over r. Now, when I divide y over r by x over r, that's the same thing as taking y over r and multiplying by the reciprocal of x over r. And you can see at this point that the r's cancel, which leaves me with y over x. But notice that y over x is tangent theta. So we have now got another trigonometric identity that says that tangent of theta is always equal to the value of sine theta divided by the value of cosine theta. And what's really cool about this is that we're going to be able to replace tangent theta with sine theta over cosine theta. Or if we ever see sine theta over cosine theta, we could replace it with tangent theta. Now, what if we were to flip these around and we were to take cosine theta and divide by and we divide by sine theta? Well, it would basically be the exact same thing here, which is y over r, or x over r rather, x over r divided by y over r. And by using the same process of multiplying by the reciprocal, this ends up giving us x over r times r over y. And likewise, the r's cancel, which gives me x over y. But x over y is cotangent theta, so we have another identity. The other quotient identity is that cotangent of theta is equal to cosine of theta divided by sine theta. And if we now combine together the reciprocal identities and these two quotient identities, it should make sense that if tangent theta and cotangent theta are reciprocal functions, that if tangent theta is sine theta over cosine theta, cotangent must be its reciprocal. So that shouldn't be too surprising. But notice that in this particular case, we now have a few more identities. Now that we've got all of our reciprocal identities, Pythagorean identities, and quotient identities, it's always a good idea to make sure that in order to memorize these and know these and be able to understand why these work, create flashcards so that you can make sure that when these show up, you recognize them a lot more quickly. Now, I would like to just revisit real quickly this last example where we ended up using an identity. Remember that we ended up having sine theta and cosine theta by the time we got to here. And then it was our job to find tangent theta. So the only identity that we had in order to find tangent of theta was to be able to use, I just realized that I made a mistake, so I'm going to revisit this here. I made a large mistake here. So notice that I get 45 over 25. So when you take a look at 45 over 25, that becomes 9/5, not 9. That was my mistake. I should have checked that earlier. 9/5. Which means when I subtract 9/5 from 1, I end up getting 5/5, so 4/5. So this is going to be 4/5, which means that this is incorrect. So I can revisit this now. And this is going to be 2 over root 5. So if I now multiply by root 5 over root 5, that means the tangent of theta is going to be the negative of 2 root 5 over 5. I'm sorry for that mistake. We all make mistakes and we learn from them. Failure is not a problem. So that actually becomes negative 2 root 5 over 5, which means that if we take a look at cotangent of theta is simply the reciprocal of tangent theta. And since we saw the tangent of theta back here had 2 over root 5, taking the reciprocal just automatically moves that up to the top. So that means that the reciprocal is root 5 over 2. But I know that it's negative. So now this should be correct. Okay, so now the problem is corrected. But I do just want to make sure that we see that in order to find tangent of theta, we used secant of theta by using the Pythagorean identity. But now that we know these quotient identities, notice that in order to find tangent theta, all I needed to know was sine and cosine. Since I already knew sine and cosine, I could have simply taken the quotient of those two And notice the 3's would have canceled, giving me -2 over root 5, which automatically is -2 root 5 over 5. It's our job to just use whatever identities are allowed, but also whatever identities we feel are going to be easiest for that particular problem. So now that we know the reciprocal identities, the Pythagorean identities, and the quotient identities, which are showing relationships between the trigonometric functions for any angle, we're now going to be able to find values given certain ratios.